Okay. Okay, so this is the math, slightly more rigorous math background that you need. Whatever the rest of the things will be more geometrical and intuitive. Okay, so let's start by looking at linear algebra, because of course when we look at convergences, it's not convergence of sequence of numbers. We should also talk about convergence of sequence of vectors or some neural network coefficients which is of size 1 million by 1 or 10 million by 1, right? A huge vector. What do you mean by that vector converging to something, right? So in order to understand those, we need to know the notion of vectors, we need to know the notion of matrices and so on, right? So let me start with one interesting problem in data analysis or machine learning, which will sort of motivate us to study more about linear algebra or matrices. Okay, so this problem is about making the problem simpler in data analysis. Okay, so we saw this problem of classification, right? So you have some, so I'm assuming that you know some notion of higher dimension, right? So you take some 100 numbers together and write it as, you can think of it as a vector, right? So you have, let's say, so many points in higher dimension, and there are the other points, let's say non-spam, again 10,000 dimension vector. I have all these points, right? But typically I don't want to work in 10,000 dimension space. Why? Because computation wise you have 10,000 numbers to deal with, right? So I want to bring this down. Suppose I want to share this data online, right? So I don't want all the 10,000 numbers to be there. Each component here is like 10,000 numbers. Now what do? How do you reduce? Maybe you can knock off a few entries, right? That's one way. You may think that certain words will never appear, maybe we'll throw away those numbers. But there is no systematic way of throwing numbers, right? And what else? So even if you do that, right, so what will happen, suppose I have, let's say in 2 dimension, let's say x comma y. If you drop off y, you will get this point x, right, in lower dimension, this one number, right? Similarly, if you knock off a few numbers in these components in these vectors, then it will go to a lower dimension. What might happen is you have spam here on one side, non-spam on the other side. When you pull it down to a lower dimension, it can mix up, right? The moment it mixes up, there is no way by which you can say that, okay, something is spam and something is non-spam. Do you agree? For example, if you project, let's say, I'll also, just for the sake of, I'll write like this. Now if you project, what will happen? All these points will be, let's say I'm going to project to x-axis, all these points will be here, right? All the other points, right, for example these points will also come and sit here, right? So everything is mixed up. So if you just look at these data points, you will never be able to say that, one is spam and one is non-spam. So there is no point in reducing the data points here, right? Because you can't solve the original problem. What is it that you have to do? You have to project, or you have to bring it down to a lower dimensional space, but in such a way that these two are separated, right? Is that clear? So how do you do that? Well, you take a vector, let's say 10,000 dimension, you reduce it to 1,000, but if you take the 1,000 dimensional vector corresponding to spam, 1,000 dimensional vector corresponding to non-spam, and look at the distance between them. Well, what do you mean by distance of two vectors, right? That's another question. How do you measure distance? How do you measure distance in 10,000 dimension space or 1,000 dimension space? Any idea? Huh? How do you measure distance between two vectors? Huh? That's a similarity, right? Not the distance. Huh? Norm of the? Okay, so what norm you will pick? Okay, so that's called Euclidean norm, the usual distance, right? There are several other ways by which you can measure the distance, which will be quite useful in data analysis. Okay, so not just the Euclidean distance, some other distance will also be useful. Okay, so in general, you need to know how do you define distance between two vectors, how do you project these vectors, right? This is a very practical problem. Do you agree? I mean, It's not some very abstract problem that nobody wants to solve, right? Only, you solve it for fun, right? So this is very useful and it's also fun, right? So you need to see how you bring down the data points to lower dimensional. So this sort of motivates us to study vectors and what do you mean, what are the properties and how do you, what do you mean by projecting or bringing down the dimension and so on, right? And what do you mean by dimension, right? Some of these things we'll quickly go through. Uh, so I think you might have taken, you have taken linear algebra, right? So what all have you studied there? Maybe depending on that, I'll modulate whatever I wanted to say. Hmm? Yes. Can somebody tell me? Can somebody tell me online people? Not many actually, only 17. Huh? Yes. Hmm?
Hello, sir.
Yes.
Sir, basically in linear algebra, we have studied about the simple systems, I mean systems of a solution till now, and and how to diagonalize it. So, and what are the requirements for that?
You're a grad student or no, right?
No, sir.
Okay, good. Okay, it's Saurav, is it? Okay. Hmm. Okay, so okay, so now let's look at anyway. It will be a recap. So, how many of you know what determinant is? What does it signify? You know how to compute determinant, right? How do you compute determinant? Well, one way is you take this element and look at the determinant of this, that you take this element, and if it is 2 cross 2, then you multiply and subtract, and very complicated. And if you look at the formula, it will be summation over all permutation minus 1 power blah 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 blah, right? So very complicated beast, right? So, but what is the intuition? I mean, what does it give us? Any idea? What is determinant?
So the area that it gives us,
Area of what?
area of a four-sided figure, so parallelogram or something.
Okay, so this is what it is, right? So for example, I take 1, 2, 3, 4. Okay, this is my matrix, right? What is determinant? 1 times 4, 3 times 6, right? So it corresponds to you. You can think of each of these as vectors, right? You have one vector like this and the other vector as like this. You form a parallelogram. The area of the parallelogram is your determinant. Okay. So in 3 dimension, what happens? If you have a 3 cross 3 matrix, it's a parallelopipe, right? Then it's not the area, it's the volume, right? In n dimension also it generalizes. So in fact, if you start looking at what are the properties of the area of a parallelogram, and if you generalize that, you get that complicated, formula for determinant. Okay. Anyway, so what what I'll try to or I attempt to do here is, of course, look at linear algebra again, but give some intuition along the way. Okay, so first of all, okay, so let's start with linear algebra. Okay, so first of all, what is the basic notion in linear algebra? This is about vectors, right? So let's start with 2 dimension. Let's observe a few things. Okay, so what is a vector space? You guys know? Huh? What is a vector space? I'm sure whoever taught you would have rigorously defined what a vector space is, right? What is a vector space? Huh? No one? Come on, guys, you should, at least somebody should answer. So you are in third year BTech IIT, so you should know what a vector space is. Huh? Not necessarily, right? So vector space need not be Euclidean. Come on, this is like you just take vector space and say set of all vectors. No, a space of all vectors. No. Okay, so you had a definition, right? We say that set V is a vector space over R if blah 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 blah, right? So now, well, it's very hard to remember those, right? So how do you remember those? Well, instead of remembering, let's see what a vector is in two dimension, or the vector that you would have studied in your pre-university or high school, right? So you have two components, right? For example, x and y, right? Do you agree? This is an example of a vector, right? So we call this as a vector. Now let's try to understand how this space behaves, right? It's all the 2 points x, y, x and y are numbers, right? So how does it behave? Now, what is the first thing that you can observe? So if you want to study this whole the vector space or the vectors, what are the kind of operations you do? The first thing you do is addition, right? I want to add two vectors. Maybe this is x dash, y dash. I want to add two vectors. What else I need to do with vectors? I want to shrink the vector or elongate or reverse, right? These are the operations, right? So I start with two things, right? So first is plus. I should tell how to add vectors. Very easy, right? How do you add these two vectors? Parallelogram, whatever you form the parallelogram, this is your addition. Actually, this point will be x plus x dash, y plus y dash, right? This is a very simple way of adding two vectors. This is how you define, right? This is how I'm going to add two vectors. Now, this plus is different from this plus, okay? So these are all subtle things that you should keep in mind. What is this plus? This is the usual addition of numbers. This plus that I'm going to talk about is the addition of two vectors. How do you define that? Through this, right? Is that fine? Okay, so basically x comma y plus x dash comma y dash is, I'll use x, maybe I'll use this plus x dash comma y. Okay, so I have to use y dash. So this is the definition of this plus. Okay, this is how defined. So you know how to add vectors. What else you need? Multiply. Of course, I cannot multiply two vectors. Doesn't make sense, right? It doesn't lead to anything interesting. So I want to, let's say, elongate or whatever, right? So how do you do that? You take a number alpha, right? Multiply by xy. Well, this multiplication is not the usual multiplication, okay? So it's a different multiplication. How do you define this? Alpha x, alpha y. Very easy, right? So it's like, you understand, right? Okay. Now with these two operations and numbers in mind, right? R, right? Because we did all the things. For example, it's a bunch of numbers and so on, right? So, for example, how do I take a vector and make it? Let's say I can increase the length or decrease the length by multiplying it by a number. Okay, so what are the ambient space here? You have a bunch of vectors like x comma y, x belongs to R, y belongs to R. That's the vector space, right? And what are the two things you have? Of course, it's over R because I'm going to change the length using numbers. Okay. What else I need? I need a plus. How do I add vectors? With this, let's try to understand what are the properties, right? So if you take two vectors and add them, you know how to add. What do you get? Get another vector, right? Where does it lie? Same space, right? So for example, I call this space or the vector space as R2, okay? It is all the points, well, it's a set, right? X, Y, such that X belongs to R, Y belongs to R. This is my space. This is a vector space. It's a two-dimensional, whatever. I haven't defined dimension, but this is your vector space, right? Now, what are the properties? The first thing that we observed is that if you take two vectors, let me call V belong to R2, implies you know how to add vectors, right? U plus V, which is same as V plus U. You can check that, right? Because the usual addition commute, so belongs to R2. What is this called? It's called closed under addition, right? Well, this is a very important property to have, because if you add two things, it goes out of space, and I mean, there's no point in adding, right? So you cannot, without thinking about anything, you cannot add. Okay, this is obvious, right? What else you have? Of course, there is a zero vector, right? What is this zero vector? 0, 0. Okay. Of course, you always have a zero vector. What is the third thing? You take any vector, there is an opposite vector. When you add them, you get zero, right? That is also another property, key property. So for every v in R2, there exists a u in R2 such that u plus v plus u is 0. Okay. What do you call this u? It's additive inverse of v, right? Minus v. That's what we call. Okay. What is the other thing that we have about vectors? We just come up with something, no, some properties. Huh? Multiplying by? No, I can multiply a vector with a number. That I can do, right? So that means I can increase the length or decrease the length, reverse the length, and so on, right? So I still get another vector, right? For every alpha, let me write this in maybe for every alpha and v in R2, alpha times v belongs to R2. I can always change the length without any problem. Anything else? Now I can take three vectors and I can add the way I want, right? It doesn't matter how you add. So for every u, v, w in R2, u plus v plus w is same as u plus v plus w. It doesn't matter how this associates. I mean, it doesn't matter, right? What else you have? I know it's boring, but we will write all the things at least once. Okay. So what else? Anything else that we can write? So for every u, v in R2, alpha in R, alpha times u plus v is alpha u plus alpha v. Okay. This is another. You agree? Anything else? Yes. Anything else? Did I forget anything? Okay. 7. Let me see if I have forgotten anything. So one more thing. So this is another boring stuff. So 6, 7. For every u in R2 and alpha beta in R, alpha plus beta times u is alpha u plus beta u. It doesn't matter. So you can take a bigger number and multiply the vector, get a very large vector, or I can take the vector, multiply by a smaller number, multiply the same by some other smaller number and add them, right? Doesn't matter. Okay. Okay. So now homework could be to check if I have missed anything. Okay. So probably if I had missed, I can write it, but it will be boring. So now what I can do is I can change this to R3. What will happen? Z. All that I have to do is this, right? Nothing changes. Okay. Still the same property. Okay. R for Rn general. Well, why to restrict to Rn, right? So I will replace this by a symbol. Okay. So what I'm going to do is I'm going to replace this by some V. Okay. So V, and V. Okay. Right. So you take any set V, we call it as a vector space. Of course, you should always have this alpha, right, which is a number. So if we say that it's a vector space V over R if all these properties are satisfied, right? Now it need not be vector. For example, okay, so now since we are running out of time, so I'll just give a couple of examples, interesting examples. So you look at this vector space V, which is set of all A, B, C, D. What is this? Such that A, B, C, D belongs to R. What is this? This is the set of all 2 cross 2 matrices, right? How many of them are there? Yeah, uncountably many, right? Do you agree? So now, is this can I think of matrices as vectors? Yes. Why? You take two matrices. I know how to add them. So if I add 2 cross 2, 2 cross 2 matrices, I'll get another 2 cross 2 matrices, which is already there in alpha. I know how to multiply alpha with matrix, right? It's alpha A, alpha B, alpha C, alpha D. That will be 2 cross 2 matrix, right? That will be another 2 cross 2, so it's closed. So you can check that all the properties are satisfied. Do you agree? Right? There's nothing strange about this, right? Of course, you have 0, 0 matrix also. Okay, not a interesting one. Can somebody give me an interesting example of a vector space? Yes, anything? Okay, so let me use this thing, a naught plus a1x plus a2 x squared, such that a naught, a1, a2 belongs to R. What is this? I'm collecting all possible second order polynomial in a basket, that is P, right? Now, do you think this forms a vector space? Yeah, you take two order second order polynomial, add them, you get another second order polynomial, right? For every second order polynomial, there is a negative second order polynomial. When you add them, you get 0 polynomial, which is 0 plus 0x plus 0x squared, right? Which is 0 basically, right? And then what else? It doesn't matter how you add two polynomials, it commutes, right? And it satisfies all the properties. Do you agree? So now, instead of studying vector space like R3, Rn, we can study a vector space V, right? So which has a very general property. So what abstraction does is, instead of writing a book for Rn, book for set of all polynomials, book for something else, you just write one book called linear algebra, right? So which deals with everything. Do you agree? Okay. So now one more example. This is another. This is set of all function from 0, 1 to 0, 1, okay, such that f of 0 equal to f of 1 equal to 0 and f is continuous. Okay. What kind of, you know what this is, right? So you have a function from 0, 1 to 0, 1. It is continuous. At 0, it should be 0, right? And 1, it should be 0. So that's such collection of functions. Do you think this is a vector space? Yes or no? Yes or no? Huh?
No.
Why do you say that it's not a vector space? It's not.
Suppose we have some addition, which is like 0.7 plus 0.7. So
Okay.
it will go out of bounds.
Okay. Now I'll do this. Is it now? Can you say? Is this a good catch? Yeah. So now, do you think this is a vector space?
Yes.
Right? You know how to add two functions, right? The usual addition, right? You take two functions which satisfy this. If you add them, if you add two continuous functions, it will be continuous. We have already seen that, right? We haven't proved, but that's an exercise. So it's closed under addition. For every f, there is a minus f also. Minus f is continuous. When you add them, you get 0, right? It doesn't matter how you add. F plus g is same as g plus f, right? Alpha plus beta times f is same as alpha times f plus alpha beta times f. So it satisfies all the properties. So this is also a vector space, right? Interestingly, vectors is not just, we started out with the usual vector that we can see, and then generalize that, but that generalization included a lot other things, right? Therefore, if you understand, for example, this simple picture here, right? So this simple R2, you will also end up understanding a lot about various other weird things, right? You can say a lot about other things also. For example, Fourier series, right? So you can think of that as, those who have studied that, you can think of that also as some sort of each basis as your vectors and so on. We'll see that. Okay. So now in the next class, what I'm going to do is I'm going to generalize this, meaning I'm going to write a proper definition for a vector space, and then we will see other things like linear independence and few other things that we need for us to look at other aspects of data analysis or mathematics for data analysis. Okay, this will be a few classes. I mean, it's longer than calculus, but very important. Okay, if you have any questions, feel free to ask. Even if you have questions about applied things like pure engineering, or if you want to understand certain things more clearly, feel free to ask questions. Okay, I'll stop here. Yeah, so we'll meet next week.